Welcome to this video on the binomial distribution, part 3. After watching this video, you should be able to write an inequality containing the random variable x in a binomial distribution example, and use our guru to calculate the probability p of x of an event in a binomial distribution using inequalities. If you have not already done so, please watch my videos entitled Binomial Distributions Part 1 and Part 2 before proceeding with this video. Binomial distribution, a note about checking the 4 requirements of the binomial. Every time you work a binomial distribution example, you should go through the 4 requirements of the binomial and make sure the problem you are working on meets all 4 requirements before proceeding with the problem. The lesson on meeting the requirements for the binomial was covered in detail in part 1 of this video. For the examples in this video, we will assume we have already checked these 4 requirements and verified that each example is a binomial distribution. Defining variables of the binomial distribution. The letter n is used to represent the total number of trials. The letter p represents the probability of success. A lowercase x is used to represent the number of successes in n trials. In part 2 of this video, we learned how to use the binomial calculator in our guru to evaluate equalities involving x. For example, x equals 0 or x equals 1. In this video, we will be using inequalities in the binomial calculator. For example, x is less than 2, x is greater than 4, x is less than or equal to 0, or x is greater than or equal to 3. Inequalities and binomial probability. Some binomial distributions will ask you to find the probability of more than one value of x at a time. In order to be able to answer these questions, you should be familiar with the following terminology. At least means greater than or equal to. At most means less than or equal to. More than or greater than means greater than. Less than or fewer than means less than. Let's take this example. A coin is flipped 5 times. What is the probability that the coin lands on heads more than once? The possible values of the binomial variable the binomial variable can assume are x equals 0, 1, 2, 3, 4, or 5. Which of these values are included in more than once? Well, more than once means it could happen twice, 3 times, 4 times, or 5 times. So x could be 2, 3, 4, or 5. So if we were going to do this by hand, we would have to compute the binomial equation 4 different times and then add them all together. So in other words, the probability that x is greater than 1 is equal to the probability that it's equal to 2, 3, 4, 5. But instead of going through all this work and calculating that probability 4 times, we could simply just go into our guru and use an inequality. So let's use this example and work through our steps. Step 1, remember, is to check the 4 requirements of the binomial. Then we have to define success. Well, in this problem, we're talking about a coin landing on heads, so we will define success as getting heads in the coin flip. Then we have to identify n, p, and x. So remember, the number of trials is 5, so n is 5. The probability of success, meaning the probability of getting heads on a fair coin when I flip it, is 0.5 or 1/2. But what about the number of successes? This is where it gets tricky. How can I write that not x equals 1, but x is more than 1? Well, I have to use the inequality sign greater than. So I would say x is greater than 1. So now it's time to take these values and put them into our software. So once I'm in our guru, I'm going to click on probability simulation, and then I'm going to click on probability, probability calculator, and discrete. When I do that, the screen shows up. Notice that the binomial is the default distribution, which is what I want. So remember, we said that we're going to flip the coin 5 times and that the probability of success is 1/2 or 0.5. So this is where the process differs from the previous video. In the previous video, we always selected equal, and then we would type our x value, for example, equals 1. Now, we don't want equals 1. We want more than 1. So we want to do above 1. Now, I want to draw your attention to this little box here because it's very small and insignificant and easy to miss, but it is very, very, very important. So just for the sake of demonstration and argument, I want to show you what happens if I leave this box checked. You can notice when I hover over this box with my mouse, the words show up include the value. Well, what does that mean? That means that I'm including the value 1. So I'm not really getting greater than 1. This is actually giving me greater than or equal to 1. But you might be confused, you might be a little bit overwhelmed. So what we're going to do is we're going to click on this graph button and we're going to preview it, and then the graph is going to help us to visualize what we just asked the computer to do. So remember, in that previous slide we said the probability of getting heads more than once is the probability of 2, 3, 4, or 5 heads. Notice, right, we really don't want to include this 1 if we're just saying greater than 1, because 1 itself is equal to 1, it's not greater than 1. So that's why I really strongly recommend showing yourself the graph to make sure that you really got what you wanted. So let's go back to our menu, and we're going to uncheck this box. So we want above 1, and so we're not including 1 in that inequality. So when I recompute this, now you can see 1 is not included in this inequality. So we're just finding the probability of 2, 3, 4, and 5. Okay, and that probability is 0.8125. So again, the most important, or possibly the most frustrating part of this, arguably, right, is remembering whether or not to check this box. And again, use this graph to help you visualize and check yourself and make sure you are computing the equality that you mean to compute. So the probability that the coin lands on head more than once is 0.8125, or 81.25%. Let's do another problem. This time we're going to be rolling a fair 6-sided die. A person rolls a die 10 times and records whether or not a 6 was rolled. What is the probability that a 6 was rolled at least 4 times? So remember, our step 1 is to always check the 4 requirements of the binomial. Then we have to define success. In this case, we're interested in whether or not a 6 was rolled. So success is going to be defined as rolling a 6. Now we want to identify the variables n, p, and x. So n is the number of trials, which is 10. The probability of success in this case is 1 over 6, or 0.1667. The number of successes here, it says at least 4 times. So try to pause this video and write down the inequality, and then see if you are correct. So let's think about what at least means. So in real life, right, you have to be at least 21 to legally drink. You have to be at least 18 to be considered adult. So what does that mean? Well, if I have to be at least 18 to be an adult, that means I have to be 18 or older. If I'm 17 years old, right, then I'm not technically legally an adult. Okay? So at least means greater than or equal to. So in this case, I want my x value to be greater than or equal to 4. So now that I have all of the values of my variables, I can plug them either into the binomial formula, or I can plug them into our guru and calculate the probability. So notice in our guru, I already have this binomial window open. Now I could open another window, but an easier thing is just to edit the values that are already here. So remember, we said we have 10 trials because we are rolling a die 10 times. And again, the probability is 1 over 6. So I'm just going to type a bunch of 6s and then a 7. Okay? And we want at least 4. So that is above 4. So let's just pause for a second and think about, do we want to include that endpoint? Well, we do, because why? Because it's greater than or equal to 4. So we need to check this box. So let's check this box and hit the eyeball and see what it looks like. So if I look at my graph, right, we want to roll a 6 at least 4 times, which means I roll it 4 times, or 5 times, or 6 times. So again, this graph is showing me, oh yes, I did actually calculate the probability that I meant to calculate. And you can also see here that the inequality sign, greater than or equal to 4, matches what we had on our PowerPoint. But just so you can understand, let's pretend I didn't check that box. Let's see what the result would be. If I don't check that box, look, now I'm not including the 4. And if I come up here, I see that I only have x's greater than 4 instead of greater than or equal to 4. So that is not going to be the correct answer. So I need to check the box if I want the correct probability. It seems like a small insignificant thing, but it's really the difference between the correct answer and an incorrect answer. So the answer, as you can see here, is 0.06973. So the probability that our software gave us was 0.06973. Depending on your directions, you might be asked to round to various decimal places. In this case, I'm going to round to 2 decimal places. So I will say the probability that a 6 was rolled at least 4 times is about 0.07 or 7%. Again, follow the directions for the question you're working on. So let's do another example. This time we're going to do an example that involves pacemakers. So it says a person is tasked with determining whether each of 9 heart pacemakers is acceptable or defective. Suppose the probability of a defective pacemaker is 6%. What is the probability that at most one pacemaker is defective? So again, we check our requirements. We make sure that this is an appropriate application of the binomial distribution. Then we have to define success. So in this case, the success is considered that the pacemaker is defective. So remember, in normal, everyday parlance, we consider success a positive thing. But in statistics, it's simply the presence of an attribute. So in this case, it's the presence of a defective pacemaker. So then step 3, we have to identify our variables. So the number of trials is 9, so n equals 9. The probability of success is 6%, so p is equal to 0.06. So the next part is particularly possibly the challenging one, right? So it says, what is the probability that at most one pacemaker is defective? So let's put this in everyday terminology. Let's say you're babysitting a little kid and they want a snack. And you say, okay, you can have at most 2 cookies for your snack. So what does that mean? Well, they can have no cookies, they can have 1 cookie, or they can have 2 cookies. They can't have more than 2 cookies. If they try to eat 3 cookies, right, they're disobeying you. They didn't do what you asked. So at most 1, what does that mean? That means either no pacemakers, 0 pacemakers are defective, or 1. So how do we write that as an inequality? Well, we write it as x is less than or equal to 1. So in other words, either x is 0 or x is 1. So now it's time to either manually calculate this using your formulas or use RGuru. So we're back in RGuru. I'm going to again click on the basics window. Okay, so remember the number of trials is 9. There are 9 pacemakers. The probability in this case that one is defective is 6% or 0.06. And we want to know what is the probability that at most 1, so that's below 1, is defective. So at this point, think about whether we do or don't want to check this box. So think about it, pause the video maybe, think about it, and then unpause it. Okay, I'm going to leave the box checked, and then I'm going to hit this eyeball. Okay, so remember we said at most 1, which means either 1 or 0. So that is absolutely correct, right? And if I come up here and look at this inequality here, that's exactly what I wanted. I wanted x is less than or equal to 1. At most 1 means less than or equal to. So that's exactly what I wanted, and the probability is about 90%. Again, just so you see, if I didn't check that box, and I look at my graph, now I didn't do what the problem asked me to do. First of all, I didn't include 1, right, the probability of 1 in my answer, and also you can see the incorrect inequality sign is here. So hopefully that just drives home the point how important that little box is. Let's work another example. This is example 4, die roll between inclusive. A person rolls a die 10 times and records whether or not a 6 was rolled. What is the probability that a 6 was rolled between 4 and 6 times inclusive? So, as always, we want to check the 4 requirements of the binomial, and in this problem, we're just going to assume that they have been met. Step 2, we have to define success in this problem. In this problem, we are considering rolling a 6, the success, and failures rolling any other number. So now we have to identify the variables n, p, and x. The number of trials, n, is 10. The probability of success in a fair 6-sided die is 1 over 6, or about 0.1667. The number of successes, x, is between 4 and 6 inclusive. Notice that since we are saying inclusive, we're using the less than or equal to sign. So now that we have all of our variables defined, we can either use a manual calculation, or we can use technology to calculate the probability of x. So in the binomial calculator, we will start entering our values. So the number of trials, n, is 10. The probability of success is 1 over 6, or 0.1666667. And then we want to select from this drop-down menu the word between. So we want between 4 and 6, and remember we want it to be inclusive, not exclusive. So both of these boxes should be checked. So let's go ahead and click the I, and we can see this is the probability, but remember, a really great thing that we can do is check the graph button, and then that way we can see not just the inequality right here, which matches what we had before, right, but we can also see 4, 5, and 6 are all shaded, because remember, we want to include the endpoints, meaning we want to include 4 and 6 in our results. So this is about 0.06946. So here's the probability that the technology gave us, and so we can round that based on what the problem asks for. And so we'll say that the probability that a 6 was rolled between 4 and 6 times inclusive is about 0.07, or about 7%. Let's work another example. This time we will work an example that is exclusive of the endpoints. So very similar to the problem we just did, we're still working with a die roll. So they roll the die 10 times and record whether or not a 6 was rolled. What is the probability that a 6 was rolled between 0 and 5 times exclusive? So again, this time we're excluding our endpoints. So the first step is to check the 4 requirements of the binomial. Again, we are going to assume that all 4 have been met, and then we will proceed. In step 2, we have to define success. So in this case, it's rolling a 6. Every other number is considered a failure. So now we have to identify our variables n, p, and x. So the number of trials, again, is 10. The probability of success is 1 over 6, or about 0.1667. And the number of successes, this time, is a compound inequality. Its x is between 0 and 5 exclusive. So notice, since it says exclusive, we're using strictly less than, meaning we're not including the points, the endpoint 0 or 5. So now we have to either use a manual calculation, or we have to use technology to calculate this probability. So I'm going back to my binomial calculator, and so the only thing I have to really change here is the 0 and the 5. Right, so those are the two numbers that I want to calculate the probabilities of, right, between 0 and 5. And let's just see what happens if I just hit this and I don't change anything else. So notice that this inequality, this compound inequality, does not look like what I want it to look like, right? And if you look at the graph, we're highlighting 0, 1, 2, 3, 4, and 5. We want to exclude 0 and we want to exclude 5. So how can I fix that in my menu? Well, all I have to do is to uncheck these two cute little boxes here, right? And then if, again, I put this I, right, now I have excluded both endpoints. So I have the probability that x is between 0 and 5 exclusive. In other words, the probability that x is equal to 1 or 2 or 3 or 4. Okay, so again, just to remind you, it seems super trivial and they're so tiny that you might even miss them, but you want to make sure that you are thinking about whether you want to check one or both of these boxes as you do these problems. So as you can see, the probability is about 0.82303. So that's about 82.3%. So now that you watch this video, you should be able to write an inequality containing the random variable x in a binomial distribution example. Use RGuru to calculate the probability p of x of an event in a binomial distribution using inequalities.